Today we're going to welcome you to Chapter 7, Solving Linear Systems. By graphing, specifically here in day number 1, we will talk about what a linear system of equations is today. We will also define what it means to be a solution to a linear system. But when we talk about what is a system of linear equations, a system of linear equations is going to be such that it is a combination of two or more equations. Prior to this, we've looked at one equation of a line. We looked at one inequality. Today, when we talk about a system is going to be a combination of two or more equations. When I take a look at determining whether or not something is going to be a solution, we're going to look at this line here, and what this in fact says is that if something is going to be a solution, not only does it need to satisfy the top or the first equation, it also needs to satisfy being a solution to the other equation or equations. In these cases, we're going to see two equations. We need to verify that that given ordered pair would be a solution to both. Both is the key word. I'll underline it in blue as a point of emphasis, but that needs to be in both equations. So let's take a look here at the first example. It says, tell whether or not 2 comma negative 3 is a solution to this given system. Well, what I want to do is I want to take 2 and negative 3 and plug it into both equations. I'm going to start with the top one first. So this is 4 times 2 plus 3 times negative 3. And we want to know, does that in fact equal negative 1? Does 8 plus negative 9 in fact equal negative 1? Does negative 1 equal negative 1? And we can say yes. That does satisfy being a solution to the first equation. We now need to check and see whether or not it satisfies being a solution in the second. So I'm going to substitute 2 in for x in the second equation, and negative 3 in for y in the second equation. And we want to know, when we simplify this, will that equal negative 11? As I take a look here, this is a negative 5 times a negative 3. 2 negatives will give me a positive 15. And we get, does 19 here equal negative 11? Well, this is false. So what we can state here as our conclusion is that 2 comma negative 3 is not a solution to the system. And again, that is my conclusion based upon algebraically what we just verified. In problem number 2, we want to verify, is 4 comma negative 3 a solution to this system? And again, I'll do them in separate colors just to help organize my work and make sure it's a little bit easier for you to follow. But let's first check here. If I plug 4 in, 2 times 4 plus negative 3, we want to know, does that equal 5? Does 8 plus negative 3 equal 5? Yes, in fact, that is a solution to the top, and only the top equation. We must also verify that is this a solution to the bottom equation. So I get negative 3 is equal to 1 minus 4. Negative 3 is equal to 1 minus 4 is negative 3, which again checks. What we can state then is that 4 comma negative 3 is a solution to the given system. Next up here, we're going to solve by graphing. When we want to solve a system by graphing, we'll take a look at what the graph is, and then we'll discuss where that solution would be located. So I'm going to, again, give a quick refresher and say we're going to graph this top line as the blue line. I'm going to remind you that is in y equals mx plus b form. So we're going to be graphing the y-intercept at negative 1. We're using a slope of up 2, right 1, up 2, right 1, up 2, right 1. Grab ourselves our straight edge and draw your line in as best you can. Line number 2 is also in y equals mx plus b form, so I'm going to graph my y-intercept, and I'm going to go down 2 and write 1, and down 2 and write 1, and down 2 and write 1, and then draw this line. What we want to locate here is the place or the location where the ordered pair is a solution for both equations. Well, what we're going to be looking at here is this point right here. This is called the point of intersection. It is also what we talk about the solution to the system. So what is that ordered pair there? What is that place, that location that is going to satisfy being a point not only on the blue line, but also on the red line? And that ordered pair there, if we recall and count it out, is 1, 1. How do you know that in fact 1, 1 is a solution? Please remember that you could always check your solution by plugging 1 in for x, 1 in for y, into both the top and into the bottom to verify. Let's take a look at problem number 4. Problem number 4 again says let's graph these two lines and find that point of intersection. So if I take a look at the graph of the first line, this is in standard form. In standard form, the easiest points to find are my x-intercepts and my y-intercept. And if I want to find my x-intercept, I'm going to cover up the y portion and say 2 times what number is -6? That is -3. If I want to find the y-intercept, I plug 0 in for x, 2 times 0, and negative, or subtracting what number is equal to -6, that in fact would be a +6. I can plot the x-intercept on the x-axis. I can plot the y-intercept on the y-axis. And let's see if I can draw that line better. Much better. The second line I'm going to do here in red, but I am going to remind you, just like the previous problems, these are in slope-intercept form. So I'm going to be able to graph my y-intercept, which was -5. And I'm going to use the slope of -5/3. So I could go down 5 and right 3, or because I run out of space, I can go up 5, left 3, and up, left 3. And when I do that, I am going to get these 3 points that line up nicely for me. I can draw my line in here, and again, what are we referencing as our solution? Remember that our solution is our point of intersection. So what was the ordered pair that was a solution on both, or to both equations? That is this point right here. POI stands for point of intersection, and that ordered pair there was -3, 0. We do get to see a lot of graphing. We're going to talk about graphing in slope-intercept form. We're going to talk about graphing in standard form. Those concepts are a review from previous chapters, specifically Chapter 4 and Chapter 5. Let's take a look at a few more graphs. In problem number 5, it would like us to graph x is equal to 4. I'm going to remind you here that if I just see x is equal to, I like to make my table of values and remind you that x has to be 4. And then I can pick my y values to be anything because it doesn't give me a relationship between x and y. Here's 4, 0, here's 4, 1, here's 4, 2. And we can draw that line in. The second line is y is equal to -2. When I graph this, again, it does not present a relationship between x and y. It just tells me that y has to be -2. So I can plot 0, -2, 1, -2, 2, -2, and we get the horizontal line. When we take a look for our solution is right here, right? That solution, I'm going to list here as also the point of intersection, is the ordered pair 4, comma, -2, if I count that on my graph. Problem number 6. Again, we get another problem in standard form. I'm going to tackle this one using my x and y intercept. So my x-intercept is found by letting y equal 0. And I know that if I cover up the y portion, the opposite of -6, or the negative of -6, is equal to +6. So -6, 0 is my x-intercept. And if I cover up the x portion, so let x be 0, then y has to be 3. Again, grab myself a straight edge, draw your line in there. The second line I'm going to do, again, using intercepts. What is my x-intercept in this problem? Well, in this problem, my x-intercept is, whoa, we're going to write that one down, but that would be 24. And I look at my y-intercept, and my y-intercept would be, if I let x be 0, that's 0, 6. Well, I'm okay plotting 0, 6. I'm going to have a hard time plotting 24, 0. So what could we do here to allow us to graph this? I'm going to cut and move this off to the side. Let me move both these off to the side. So one thing I can do is I can take and rewrite as y equals mx plus b. How do I rewrite this as y equals mx plus b? I'm going to subtract x. And divide by 4. That gives me y is equal to -1/4 x plus 6. That is going to be much easier for me to try to graph, because now I'm talking about going down 1, 2, 3, 4. Or sorry, let me correct that. Going down 1 and over 1, 2, 3, 4. And there is, in fact, a point that we could get to. I could probably squeeze in and do it one more time. Go down in 1, 2, 3, 4. And now, without having to change my scale, I'm able to graph both lines in the same coordinate plane with the same, what do I want to call this? Same scale on our axes. Remember, my solution here is the point of intersection. That is right here. I do want to write down what that solution is, because what we are doing here is solving this by graphing. And if I want to find that there, that point is located at 4, 5. If we are unsure if that works, all we need to do is take and plug in to verify that it does in fact work. So if you plug that into the top, that's the opposite of 4, which is -4, plus 2 times 5, which is 10. And we want to know, does that in fact equal 6? And that would be true. So yes, 4, 5 is the solution there. 2 more problems. We're going to graph the top line. Top line is y equals mx plus b with a slope of 1/1. So I'm going to go up 1, 2, 3, 4, 5 as my y-intercept. Up 1 and over 1, up 1 and over 1, up 1 and over 1. If I don't want to go up and right, please recognize I can also go down and left as well. This second line is in standard form. And when a line is in standard form, it is best to find our intercepts. So if I want to find my intercepts, I'm going to let y equals 0 and x would have to be 4. If I let x be 0, y would have to be 8. Graph those two lines, and again, we want to locate where our solution is. And when we talk about a solution is this point of intersection right here. Which is, again, if we need to count that out, that is going to be 1, 6. If you'd like to verify if you did it correctly, please plug 1 in for x, plug 6 in for y into both equations and check it. And that is like we did in problem number 1 and 2, specifically number 2, because number 2 at the start of these notes was where we said it was a solution. Last but not least here, we're graphing problem number 8, both lines. If I want to find my x-intercept here is 5, my y-intercept is -5. Again, we can find those both by plugging 0 in for y and x respectively. When I plot those, here's 5, 0. Here's 0, -5. I'm going to take a look at the second line. Again, also in standard form. I'm going to find the x-intercept and the y-intercept. The x-intercept, 3 times what number is 3? That is 1. And then if I plug 0 in for x, y would have to equal 3 as stated there. Graph that, I get 1, 0, and 0, 3. Sometimes you'll get an image here where maybe it doesn't look like it quite crosses at like a grid line. If it's not crossing it exactly at a grid line, maybe one of my lines wasn't drawn very well. So if I'd like to double check whether or not my lines are drawn well, I'm going to double check this line and see if I draw that again. It was better for a second. And then last moment I slid it off to the side. But I should notice that it is crossing right here. That first time I drew it, it wasn't quite going through this x-intercept at 1, 0. It's going through like 1 point something. So if I take a look here, my solution is in fact this point right here. What is that ordered pair there? That ordered pair there is my point of intersection, which is 2, -3. Again, how do you verify this is a solution? We can take and plug it back into the top. Please notice if we have 2 minus -3, 5 does equal 5. You can also check that in the bottom. And we get 6 minus 3 does equal 3. So again, all we did was just verify the solutions there. Again, welcome to solving a system of linear equations. We talked about what a system was today. We also were able to discuss how do you know if something is a solution and what is a solution to that system. And we also talked about graphing a system to find the solution or the point of intersection. Let's practice this, and we'll discuss again tomorrow.